All right, welcome. We're going to look at our first test review for your midterm coming up next class. What you need to do first, I'm going to pause the video, but here what you need to do. You need to open up your digital classroom. Click on classwork and open up the Desmos AP Pre-Calculus version. I want you to have that one open. That's what we're going to be using today. Once you come back online, I want you to graph this equation. I'm going to go ahead and graph it, then I'm going to pause and give you a minute to catch up to me. But that's what we're doing right now. And then we will pick back up. Type that equation in. All right, as we get started here, the first problem says the charge C of a cell phone is given by this function where this is true about the T. How many extrema does this function C have on its domain? Additionally, label any extrema as either global, local, or both global and local. What I need to remind you of on this first review problem is how to do a restriction or a constraint, whatever you want to call it, on Desmos. Does anybody remember what to do? We did this on lesson 1-4. Here we go.
Put that little symbol.
You put the squiggly brackets around it. So go ahead on your packet. So if you look back at this, you'll know how you did it. You put those little squiggly brackets just around like that. And that's what we're going to be using here in Desmos. So I'm going to put right after the 100, I'm going to put that squiggly bracket 0 less than, it's not typing. What's going on? 0 less than equal button T less than equals 6.63. My graph right now, I'm extending off the screen. I need to zoom out a little bit so I can see my graph. There's my graph. Probably zoomed out too far. That's the graph we're working with right there. How many extrema do you see on this graph now? I'm going to make sure you can see what I have typed in. How many extrema do you see on this graph? What is an extrema? A maximum or a minimum. You look for where you change direction or a starting and ending point of a graph. This graph has two. It has this, what would this point be? A maximum or a minimum? A maximum and that minimum. Now we're going to draw that over. All right, so I'm going to take this graph over and I'll draw it over here just to make it easier for myself. I'm going to make it not quite so narrow. So it seemed like it went something like that. I could make it a little bit closer. Maybe it starts a little bit more steep and then it cuts down. But either way, make sure you have that on your packet, that it kind of comes in like this, and then it went around and dropped like that. The coordinates here, we had 0, 100. And my other coordinate I lost. What was my other coordinate down here? We need 3 decimals. In AP Pre-Cal, you're always required to take 3 decimals. If your number is bigger than that, you don't have to round. You can truncate. That just means cut it off. So I'm going to have 6.629, 0. 6.629, 6.629, 0. So there's my graph. It says how many extrema does the function C have on its domain? How many extrema? 2 extrema. We have 2 extrema. Extrema means maximums and minimums. Additionally, label any extrema as either global, local, or both global and local. What is this here? What would you call that point right there? Maximum. Is that the highest point on the entire graph? So it's a global. So every maximum is always, and minimum, it's always local. It's just whether or not it's also global. You could also use relative and absolute terminology as well. This right here is a global and local maximum. This point down here, is that a global or just a local minimum? Global. So we would say this is a global and local minimum. All using the words I use that one lesson. All extrema are always relative, just the same, they're always locals, but they're not always absolutes or globals. Global and absolute mean the same thing. Okay, so global means the same thing as absolute. That's what that means. It's like absolute. Whereas local means relative. All are always relatives. They're always locals, but they're not always absolutes. In this case, they both work. Questions over how to graph with constraints, with restrictions. Any questions over that? Okay, let's move on to our next problem then. Our second problem we have here, it says the velocity of a wave of water meeting the shore is shown on the graph. Based on the graph, how many extrema does the function v have on its domain? Additionally, label any extrema as either global, local, or both global and local. All right, so this time I want to zoom in a little bit here. How many extrema does this graph have? Two. It's going to be a very common answer, and it'll be a very common incorrect answer. Jaden, how many are you saying? It does have four. Where are they? This one's obvious to see. What would you call that one? What type of minimum? Global or absolute? And if you use the word global, you would also use local minimum. This one's also obvious to see. This is also a global and local. This one's a maximum. But where are the other two? You need to remember starting points and ending points. If they're not arrows, if they're points. Starting points and ending points by definition are always maximums and minimums. So in this particular case, this would that be a maximum or a minimum, do you think? It is a maximum or a minimum. Which one? This is a maximum because it's higher than this part right next to it. So this would be called just a local maximum. And again, you could use the word relative. Whereas this point over here, this one would be a local minimum because it's the lowest point in that area. So how many total extrema? 4 total extrema. 4 total extrema. Extrema means maximums and minimums. So all that was from lesson 1-4, the first 2 examples there. All right, on this next slide, we're going to take a look at. These are putting together some of the rules that we learned about rate of change. This is lesson 1-1, 1-2, and 1-3. I've merged some of this information here. So the first thing I want you to be aware of is what these things can mean. It says here, complete the table if y is equal to f of x, which I already put that there. G of x equals this. Now let us pause for a minute. Let's focus on this g of x equals. Now, last class we talked about this 1-7. We compared the insides. On 1-7, we were doing even and odd. We had opposite x's. Now, these are not opposite x's. How are the x's related here? This x compared to this x. Are they the same value inside? No. This x is 1 less than this x, or you could say this inside value is 1 greater than this one. Said another way, we have a change of x. How much did the x change by from here to there? 1. Okay, now, what's happened to our f values? We're changing the y's. How do I know? Because we are subtracting them. So we have, I know it looks like an opposite f values, but what's happening is we're changing the y values. Right now we have some change of y values because that's one f subtracting the other. We're taking the change of y here, and we have a change of x of 1. What is the change of y? Whoops. What is the change of y divided by the change of x equal to? What's that equal to? A rock. Well, in this particular case, what is my change of x? 1. So if you had the change of y divided by 1 equaling a rock, that would mean that the change of y by itself is, the change of y would be equal to a rock. This g of x, this is the a rock equation. G of x is equal to your a rock. This is the symbols because what's happening is it's saying your x's have changed by 1 and you're subtracting your y's. That's like y1 minus, or excuse me, y2 minus y1. That's like y2 minus y1. You could think of it that way because these would be different y's since they have different inside values. So all that is a fancy way of saying a-rock. What do you think h of x being g of x plus 1 minus g of x is equal to? Any takers on what this would simplify to become? I'll give you a hint. It's g of x, this g of x, minus a different g of x. If you took one of these and subtracted a previous one, what would you get? Okay, let's go back through this one more time. What's happening with my x's? They're changing by 1. We have a change of x that's equal to 1. Up here we have a change of y's. Now the g, though, was already itself a change of y. So technically this is a change of y. How did I get that? Because what was g to begin with? G was the change y. So that means if you now are changing your g's, you're changing the change of gy. Anybody figured out what this is yet? This is equal to the change of the average rate of change, the change of the a-rock. That's what that equation is. That's just a weird way of writing it, but that is what those are. As we were going through these lessons, I gave you some relationships. Who remembers? If a function itself is concave up, what is true about its average rate of change? Always, always, always. If a function itself is concave up, what would be true about its rate of change? Not positive. That'll be an option, but this would be a wrong option. Increasing. You need to know that this would be increasing. That would be increasing. Okay, now if a function's concave up and its average rate of change is increasing, that means the change of the a-rock. So I'll give you some examples. Increasing numbers would be like 5, 6, 7, 8, 9, 10. It would be like 5, 7, 9, 13, 20. It could be 20, 25, 29, 31, whatever. If these are increasing, what's true about their change? They're positives. You need to know that relationship. We'll call that relationship number 1. You need to know this relationship. Okay, let's go down here. We have relationship number 2. This says the change of the a-rock is negative. If the change of the a-rock is negative, what has to be true about the average rate of change? Decreasing. This has to be decreasing. Now, if this is decreasing, the average rate of change, that is, if the average rate of change is decreasing, what has to be true about your function? It has to be concave down on that interval. Any question about that? All right, so now what I want to do is this. I'm going to make up a number here. Let's say these are values on an interval where x is less than 2. Come over here and add that x is greater than 2 here. I'm just making this up. This is just for an example. This is just an example now. If this is when x is less than 2 and this is when x is greater than 2, let's talk about when x is equal to 2. That's going to be right on the line. If this is x is less than 2, and this is x is greater than 2, that means you were concave up, now you're concave down. Show me that with your hands. Your first hand, show me your left hand, concave up. Now take your right hand, concave down. Put them together. That in our problem represents the value of 2. What does the point at when x is 2, what does that represent? A point of inflection. Add that if x equals 2 here, we would have a point of inflection. Right here, this would be a point of inflection. Said another way, a point of inflection is where the point where concave up meets concave down. Or vice versa. It could go concave down first if you're wondering. It could go concave down meaning concave up. But where they meet, it's called a point of inflection. Okay, now this one. If you were increasing, show me increasing with your left arm. Left arm has to be increasing. Your right arm, give me decreasing. Put them together. Where they meet, that point creates something. That's called a maximum. Very, very good. This would be a maximum. Now, a different question. This time, what if the order was backwards? What if we first were decreasing and then increasing? Let's do that. Left arm decrease, right arm decrease. Where they meet, what does that become? Minimum. So the order matters on that one. It does not matter on concavity. It does matter for your extrema. Okay, what about the last one? You were a positive number. Now you are a negative number. So I don't know how to do positives other than do one hand way up high, then another hand way down low. What comes in between those positives up high and the negatives down low? Zero, right? This is right in the middle. Zero. So put a 0 there. You need to know that relationship. Okay, last one. If, this is a whole new situation, if f of x is a cubic function, what would that mean? What type of function would describe the average rate of change? If this was cubic, what would be true about its average rate of change? Quadratic, yeah. Why would it be quadratic? You lose the highest degree. So this would be some type of quadratic function. So you'd be looking for something in the form of ax squared plus bx plus c. And what would that make the change in the average rate of change? Linear. Y'all remember that? It always goes down, which would be something in the form of y equals mx plus b. It'd be some type of equation like that. John, you with me? Okay, so I have this table. I have another table. Before we start plugging in numbers, I have one more time. We're going to walk through this a second time. Let's see it again. New situation. Look up at the top. When you see g of x equals f of x plus 1 minus f of x, what is that telling you right there? That's a fancy way of saying the AROC. This right here is the average rate of change. That's a fancy way of saying the AROC. So g of x is equal to the AROC. And right over here, if g is the AROC, what happens when you take an AROC and you subtract another AROC from it? You get the change of AROC. So that's what h of x is here. H of x is equal to the change of AROC. I'm just showing you fancy ways that it can be written. That's using math notation. All right, questions up for you. If this is linear, this time I'm going to do a countdown. I want you to fill in what's true for this box and for this box. I just gave you the rules on the previous page. I want you to write down what you think is true for this box and this box. I'm going to pause the video. All right, picking up. If the g of x is linear, this column is linear, what has to be true for this box right here? Siri, what do you got? It has to be quadratic because whenever you're working with one of these tables, anytime you go to the left, you gain a higher degree. Anytime you go to the right, you lose a degree. This has to be quadratic. What's the form of a quadratic equation? ax squared plus bx plus c. You would be looking for some type of equation like that. Okay, that's going to the left. Jamleth, if this is linear here and you go right, what's going to happen if you go right on your table? Will we gain a power or lose a power? You'll lose. So if we lost the bx, what are we left with? Just the c. What does c stand for? Constant. This would be constant over here. You need to know that relationship. That if you move left, you gain powers. If you move right, you lose powers. So that would be completing that table. Okay, here I've mixed up this table. This time I'm telling you f of x is increasing. What does that mean about f of x if it's increasing? What does that mean about g of x? The average rate of change. If you are increasing, what would this mean this is? Positive. Very good. Very good. This is positive. Why did you not say concave up? Concave up is when you move to the left of increasing. When you go to the right of increasing, it is positive. What if we go to the right of positive? We don't know. So do NA. There's nothing you can predict off of that. If you try to predict off it, you're going to be wrong. So put NA as in that's nothing to predict. Okay, how about the last one? What if the average rate of change is concave down? What would we put on the left? Not decreasing. NA, why NA? We cannot predict to the left of concavity. You don't predict to the left of concavity. Okay, what could you put on the right? If the g of x is concave down, what is true about h of x? It would be decreasing. All the blue is true. You can predict it every time. The NA means you cannot predict. That's how the patterns work. So on the previous, when you look at these, I put them the way you normally see them. Normally it goes concavity, following by increasing, decreasing, followed by positive or negative. However, they do not have to be locked in these columns. You can switch them around, but just know, concavity, you cannot predict to the left, but you can predict to the right. Increasing, you can go one left and one right. Positive, you can predict to the left, but not to the right. All that to say is I should try to apply it here of when you could apply and when you could not. So make sure you know those tables. Now let's practice some with numbers. All right, so now we're going to take a look at specifics rather than going over the theory like I just did on the previous two examples. Let's now talk about, let's actually work it through. Again, I'm leaving this up there so you can see it. If you see these symbols right here, that y is equal to f of x, and that g of x equals the f of x plus 1 minus f of x, what is that telling you that g is? I'll give you a hint right there. What is it saying g is? A rock. And so if you then change the A rock, that's what's happening here. I'm changing the A rock. If you change the A rock, what do you get? Change of A rock. That's it. The next column. Okay, let's walk through this and practice it. So if I'm going to find the A rock, what's the formula for A rock? Or yeah, I know that one's written here. What's the easier way of saying that? Change of y's divided by change of x. So on this one, how much do my y's change by? 70. Increase or decrease by 70? Increase. Put a plus 70 here. It's always better if you do a plus or a minus. Now, do the x's change by ones? No, so we have to include these. How much do my x's change by? Plus 2. The x's are always positive, so you don't actually have to put the plus, but I will there. What is 70 divided by 2? Okay, positive 35. Let's go to the next one. From negative 13 to 1, we increase by 14. What about my x's? Plus 2. So positive 14 divided by 2 is equal to 7. Good. Okay, how about from 1 to 7? Plus 6. And how about my x's? Plus 2. So it's 6 divided by 2, which is 3. Okay, one more time. From 7 to 53 plus 46 divided by 2. 46 divided by 2 is 23. Okay, what are some things that you could tell me when you look at this? Do they all increase? No, they don't. We went from 35 to 7 to 3. That's decreasing, but then we go to 23. So they don't all increase. But what else could you tell me? They all are something. Positive. These are all positive. So if these are all positive, what can you, this is the only observation we can make right now. Concrete. If these are all positive, what do we know has to be true of this? This column has to be increasing. Look at the numbers. Do they all increase? Yeah, so after stage 1, that's the only thing we could say. After stage 1. How about I color coordinate this? I'm going to turn this blue. After stage 1, that's the only thing that we could state confidently. Okay, now I'm going to go to stage 2. I can keep going because these are not constants, so we keep on going. When I check the next round, the change of A rock here, how much do my A rocks change by? 28. Increase or decrease? Decrease. You don't ever have to worry about dividing this by 2. We don't have to worry about that. That decreases by 28. How about from here to here? Although technically, I think you would actually divide that by 2. But anyways, we subtract 4. Okay, what about here to here? Plus 20. Okay. What can you tell me about these numbers? They are not constant. Are they all positives? Are they all negatives? But there is something you can tell me. These are increasing. Now, on stage 2, we'll call it stage 2. If this is increasing, what has to be true of this column? This one has to be concave up. And if this is concave up, what is true over here? Nothing. Good. We can't predict anything. You leave it. All right, I'm going to add in one more column. Because if I add in one more column, we can make another observation here. And this will just be good. And so now I'm going to have a new column right here. Oh, that's not the color I wanted. We're doing black. Let's do black column. Okay, black. Here we go. If I added in one more column, how much do I change going from here to here? Plus 24. And what about from here to here? Okay. What can you now tell me? We'll call this stage 3 here. What can you tell me about these? Constant. And not only are they constant, they're also positive. So if these are constant and positive, I'm going to slide these up so I can try to fit more in here. If these are constant and positive, what two things could you tell me about this column here? Linear and, okay, do we have to say increasing again? No, this one actually connects to there. Those two connect together. That looks like I'm saying switch places. But that positive would actually say increasing, which we already wrote increasing. We already knew that. Okay, now if this is linear, what's this column? Quadratic. And if this column is quadratic, what could you tell me about f of x? It's cubic. So all those different things you can determine at different stages along the way. Any questions over that one? All right, I'm going to pause it here or stop it here. Now, one more time, we're going to work out one of these tables. So I have it written in again up here, just so everybody's aware. When you see this g of x, all right, let me start where I need to start. If you see that y equals f of x, and then g of x equals f of x plus 1 minus f of x, what is that telling you about g? G is a rock. And then over here, if h of x equals that, what is that telling you about h? Change or a rock. So I just want to make sure you're aware of those symbols. That's what they mean. So now let's go through and work this one more time. When I look at these numbers, first stage here, notice I have some positives, I have some negatives. These are decreasing, then they're increasing. I have a lot of things going on throughout this problem. What can you tell me about here to there? What kind of a change is that? Minus 24. And what's my change of x's? Plus 3. So it's minus 24 divided by positive 3. Again, x's are always positive, so you don't actually have to put the plus on that. What is negative 24 divided by 3? Negative 8. Good. Okay, next one. How about from 2 to negative 4? Minus 6. What are my x's changed by? 3. So what do we get? Negative 2. How about from 4 to 8? Plus 12. And from 3 to 6? So it's positive 4. And then what about from here to here? Plus 30. And from here to here? Plus dividing by 3. What is 30 divided by 3? 10. Okay, when you look at these numbers, what can you tell me about all of them? These are all increasing. So if these are all increasing, what does that mean is true for this column? Concave up. And this time I want to get in order. What does that mean is going to be true on this column? Positive. I didn't do that last time. I didn't predict for the future, and I should have. That one has to be positive because of this unbreakable chain right here. So that's all proven through stage 1. Okay, let's move on to stage 2 now. What can you tell me about stage 2? How much is that increasing by? 6. What about here? Plus 6. And what about right here? Plus 6. What can you tell me about all of these? It's positive. We just proved it was already positive. We knew that it was going to be. We just proved it. And what else can we say? It's constant. Good. It's constant. So if this is constant, what has to be true about this column to the left of it? Linear. What has to be true about this column? You got it. One of the things I did not mention earlier on the last problem that we looked at, I should have, I'm going to back up real quick, is because it was cubic, we have a spot where it's concave up and concave down. I want you to go in here. Remember, to be concave up, what that means, if you are concave up, here, I'm going to go ahead and in blue. If this column is increasing and this one's positive, you could not predict anything over here. I'm going to go ahead and fill it in. I didn't fill that in. Increasing, concave up, cubic, quadratic, linear. Great. And on red, I could have said, if this is increasing, we would have known this is constant. There, I'm going to color coordinate better. So if you look back in the notes later, this makes sense. We could have predicted it in that order. Okay. And if you're NA there, it would be NA as well right there. Okay. One of the things I want to say, if you're concave up, that means you are increasing on the column to the right. That makes sense? So on this one, you see how these values are at first decreasing? You see how we are at first decreasing? This graph right here, on this same interval from these values where you are decreasing, that is where the graph would be concave down. But here I increase. So from here, it would be concave up. What am I saying? If I added in a line, what you could state about the graph is in halves about concavity. You could say, let me just divide it at 3 here. On the interval -3 to 1, this graph has to be, what's happening to these values? Decreasing. Because these are decreasing in here. Because these are decreasing, on the interval -3 to 1, this graph is concave down. But these values, what happened over here? These increased. Because we were increasing here, this interval has to be concave up, which means somewhere between 1 and 3, you have some point. What do we call it? A point of inflection. And in here, if you were decreasing and now you're increasing, what would be true in this one? Not 0. Do it with your arms. Decreasing to increasing, what'd you create? A minimum. You would have a minimum in here somewhere. And that would mean if you had a point of inflection, a minimum here, guess what has to happen over here? You have to have 0, and it should make sense. Think about it. You have a number here. Let me go ahead and cross. You have a -4 and you have a +20. What's in between a -4 and a +20? What number is somewhere in between those? 0. Yeah, 0 hits somewhere in there. So all that math should make sense. All right. Any questions over that before I leave that behind? All right. Now we're going to take a look at some graphs. Now you'll learn about this graph later in the year. This is a trigonometric graph. That's after Christmas break. You won't see this as an equation for a while, but it's a great view of a graph to come up with this question. It says the graph of H is shown. Describe the concavity of the graph of H and determine whether the rate of change of H is increasing or decreasing on each interval. So what I'm going to do here to help us out is I'm going to draw some lines, and I hope you do the same on your packet. So between F and G, like that, this is the interval. Oh, I should have stopped. What does it mean, interval? What does that mean? X values, yeah. So from the X value, we're calling it like X1 to X2 here. On this interval, would this part be concave up or concave down? If you try to match it with your hand, would your hand be upside down to match that piece or right side up? Upside down. So what does that mean about that interval from F to G? Oh, we're just concave up or concave down. That's what we're doing with our hands there. It is concave down. We are concave down. If you are concave down in here, the next question, let's read the problem closely. Describe the concavity of the graph of H. So in case you didn't realize, this is H itself. This is the graph of H. It says it right there. The graph of H is there. If this is the graph of H, if we're concave down, now we want to know the rate of change of H. The rate of change, the A rock. What would be true about the A rock from here to here? It's decreasing. As you go along, the A rock would be decreasing. So it's concave down, and they say rate of change here. No, I'm just going to say the rock. I'm not doing the word average because they don't include it in this one. And the rock is decreasing. How did y'all know decreasing? Because the function itself is concave down. Good. All right, let's take a look at the next interval. So next interval, we're going to look at, let me just copy and paste. We're now going to focus on G to J. From G to J. I guess I'll need 2 lines. From G to J. So I want you to think about your hand here. From G to J. If you were going to do that, would you do upside down with your hand or right side up? From G to J. How would you put your hand on that? Right side up. What does that mean about its concavity? It's concave up. And if you are concave up, what does that mean about the rate of change? Increasing. So we are concave up. And the rate of change is increasing. Okay, how about J to K? If you were to put your hand on there, is that concave up or concave down? That is still concave up. So if we are still concave up, what does that mean about the rate of change? If you are concave up, if you're concave up, what's true about the rate of change? Increasing. Finally, K to P. If you were to put your hands on the graph from K to P, which way would you have your hands to try to cover up that graph? Would you go right side up or upside down? Upside down. What does that mean it is? Concave down. And if we are concave down, then what is true about the rate of change? Decreasing. Hopefully you're noticing the importance of knowing how they're connected together. The graph is concave down, and that means the rate of change is decreasing. Now, I want to try to mix it up. I want to use different words to see how good you are at your vocabulary. So we're going to take a look on these. This next one says, on which interval is the function increasing at a decreasing rate? So now you have to really do some thinking here. Where is the function increasing? And you need to think about, what does that mean? And then at a decreasing rate, what does that mean? I'll give you a hint. You have heard the word rate before today, probably 10 times. When do I say rate? The rate of change. This is saying you have a decreasing rate of change. Instead of doing you want to do A rock or rock? You want to do rock? Yeah, because they don't say average. You have a decreasing rock rate of change, but the function is yet increasing. I want you to think about what is true here. I'll give you a few seconds. I'll pause the video. Okay, now that I've given you some time to think, what do y'all think? 5, A, B, C, or D is what I'm wanting. 5, 4, 3, 2, 1. D? I agree. It is D. All right, I'm going to circle up D here, and let's talk about why it is. Okay, one thing at a time. Let's start first with the function increasing. What does it mean about the function increasing? Going up. From F to G, do we go up? No, here the function decreases, so it is out. There it decreases, okay? How about from G to J? We are still decreasing, so that is out. How about from J to K? We're increasing, and K to P? Increasing. Both of these are increasing. So both of these are increasing. We're still both good. All right, now the last thing it says here, it's increasing at a decreasing rate. That means your rate of change is decreasing. What else could you say instead of the rate of change is decreasing? What also has to be true? The graph, if the rate of change is decreasing, that means the graph is concave down. On J to K, what is our graph here from J to K? In this window, we are concave up. So that would not be the answer. This one is concave up. So C is out, therefore D has to be the answer. Just to check it real quick, from K to P, is it concave down? Yeah, this would be concave down. So make sure you understand how that works. I got a couple more of them just to make sure you know how it works. Let's try the next one. Again, if you're watching at home, just pause the video, give yourself a chance to think about it. But in here, you're thinking on which interval is the function increasing at an increasing rate. I'm gonna pause the video. All right, count answers in 5, 4, 3, 2, 1. C is correct this time. Y'all are catching on. What does it mean for the function to be increasing? What does it mean for the function to be increasing? The graph itself, the function is the graph has to be going up. So what are we doing there? Down. What are we doing here? We're still going down. Those two are out. It has to be one of these two. These two do increase. That's increasing. That's also increasing. So it's one of those two. Increasing rate. What is the same thing as rate? Rate of change. If your rate of change is increasing, what has to be true about the function? The function is concave up. Remember, the rate of change on the tables came after the function. So the function is concave up. On this interval here, from J to K, what is my function? Concave up or concave down? This is concave up, whereas on this interval, we are concave down. So therefore, the answer has to be C. Okay, I have one more for these to try. On which interval is the function decreasing at an increasing rate? I'm not going to pause it as long this time, so think quickly. All right, 5, 4, 3, 2, 1. Y'all are all getting B? Okay, for the function to be decreasing, just to fill out the notes here, for the function to be decreasing, what does that mean is happening to the graph? It has to be moving downward. So the first two are moving downward, but the last two intervals are increasing up. So these would be out based off that. Those are increasing, these are decreasing. Now, what's it mean just when they say increasing rate? What is the rate the same thing as? The rate of change. If your rate of change is increasing, what does that mean about the function? The function is concave up. So on which interval? So what is true from F to G? Tell me about my concavity here. This is concave down, whereas this one is concave, up. Okay, so there's another connection, more practice. Make sure you know those. I've hit those a bunch of times. Hopefully, you're realizing it's very important that you know that relationship there. All right, so that wraps up this section. All right, the next section we're going to look at is a review from last class, lesson 1-7. This is where we dealt with end behavior. End behavior. Now, I want to make sure everybody's aware this limit right here, when x is going to infinity, I want you to just tell me left or right. What direction is this? Right. So this limit right there, whoops, would be called the right end behavior. This limit is called the right end behavior because that's what's happening on the right side of the graph. That's what that one is. This one over here, when x is going to negative infinity, what direction is that? Left or right? Left. This is called the left end behavior. Remember, polynomials will only do one of three things. They will either rise, fall, or get flat as you go to the far left and far right. So according to this limit over here, what's happening on the right side of my graph? It's rising. We rise to the right. So I'm going to just go from the origin, doesn't really matter, and I'm going to make my graph rise to the right. According to this limit, what happens on the left? I didn't hear you because of the bell. What do we have? What happens on the right? Or the left? I'm sorry, the left. It also rises to the left. So back from the origin, I'm going to go this way. Okay, what can you tell me about my degree on the end behaviors? You can't tell me about the inside. We have no idea what's happening on the inside. But what can you tell me about my degree here when you look at it? An even degree. How'd you know that? Both sides go up. What else could you tell me about my leading term? A positive leading term. Because they're both rising and not falling, it's a positive leading term. Okay, look at your answer choices. Based off those two pieces of information, you need to be able to find the answer. Could the answer be A? No. What's the problem with A? Here's my leading term. It has two things wrong with it. What's the two things that are wrong with it? It's negative and it's odd. Both of those are wrong. So those are wrong for two reasons. Okay, what's my leading term on the next one? Negative 4x to the fourth. Does that work? No, it's out. Those are both out. Okay, what's my leading term on C? 2x cubed. Does that work? No, why not? Odd degree. Okay, what about the last one? 4x to the sixth. Does that work? Yes, that's the answer. So the answer would be D here. Okay, I have another one of these. Okay, let's go through this again. The first limit that it shows us here. Remember, I didn't say this a second ago. A limit. That doesn't tell you where the graph is. A limit tells you where it's going. That's what it represents in math, like an arrow on the graph. That's why it says X arrow there. This limit this time, is this the left end or right end behavior? This is the left end behavior. Very good. How'd you know it was the left end behavior? Because X is going to negative infinity. So we're talking about the left side of the graph here, the left end behavior. On this graph, what happens as the graph goes left? It needs to rise. On the left side, we need to rise. So I'm going to go from the origin. You don't have to. But I'm going to go from the origin. We're going to rise on the left side. Now, this is the right end behavior this time. How do I know it's the right end behavior? What am I looking at? The X value. That tells you left to right. This is the right end behavior. What is happening on the right side of the graph? The graph is falling. So I'm going to go from the origin and make it fall this way. What observations could you make from the end behavior? What's odd? The whole function's odd? The degree. There you go. We can make the observation that the degree has to be odd. What other observation could you make if this is an S curve that's decreasing? A negative leading term. Or coefficient is actually be a better word to say. A negative leading coefficient. I should change it on the previous slide. Negative leading or coefficient. That's the better word. That just means the number in the front. Okay. So this is a negative leading coefficient. All right, let's go through them again. Answer choice A. What is my degreed, or what's my leading term? Negative x cubed. Good or bad?
Good.
Good. That's the answer. That was quick. What's the problem on B? Even degree. That's the problem here. This is an even degree. What's the problem on C? Positive leading coefficient. Positive leading, I'm just going to say lead coefficient. And what's the problem on D? Positive and even. It has two problems. Positive. This time I'm going to just say LC leading coefficient. And it's a even degree. That's the problem with those. Therefore, the answer has to be A. Cool on that skill? That's from lesson 1-4. Okay, so to finish up lesson 1-7, we did limits, and then we talked about even, odd, and things like that. What does it mean? Catch this. Be very careful in your vocabulary here. For a function to be even. If the function itself is even, what does that mean? All exponents are even. Okay, I hear y'all say that. That was not the definition I gave you. That's true. That is a true statement. All exponents are even. That is a true statement. What was the definition I gave you? That's what you need to remember, the definition. Opposite x values. I'm going to just type this in so it's easier to read. Opposite x values. Produce. What's the math word for same? Equal y values. There you go. So as an equation, that's the definition right there. As an equation, it would look like this. If you had f of negative x, that would equal f of positive x. The function f is the same with opposite x's. So these two statements are one and the same. They mean the same thing. When people do like double arrow like that, it's a way in math to say they're congruent. They mean the same thing. So those two statements mean the same thing. Okay, what does it mean for a function to be odd? All right, I'm going to copy and paste. If you right click with your pencil, choose paste, just change it, word equal. Bad joke, okay, I'll tell that joke next period. Opposite x values produce opposite y values. So this is where you have f of negative x equaling the negative f of positive x. This was a true statement here. All exponents are even. What is it true? What is the true statement if it's odd? All exponents are odd. And remember, a constant is like an exponent of x to the power of 0. So it will not have a constant. Odd functions will not have a constant. Okay, last one. What does it mean if a function is neither even nor odd? Opposite x values, whoops, do not produce equal nor opposite y values. So they just produce something random. There is no symbol that we would do here. I mean, you could say it does not equal symbol for both of these. That f of negative x does not equal f of x, and it does not equal negative f of x either. What does it mean, practically speaking, if you're looking at the exponents? Both even and odd exponents. Good. You would have both present. Okay. All right, our one question here so far, our first question from lesson 1.6. I haven't hit anything from 1.6 nor 1.5. What does it conjugate pairs mean? Truthfully, 1.5 and 1.6, they were one lesson that I broke into two. It's 2 parts. That's what those were. It was a 2-part lesson. What does it mean to have conjugate pairs? Can you give me 2 different examples of factors that are conjugate pairs? What does conjugate pairs mean? A positive and a negative. That's it. That's a positive, and a negative version. And negative version. So, for example, if we were talking about, do you remember what types of answers have the conjugate pairs? There were 2 types, imaginary and irrational. Okay, if we were talking about imaginary zeros, I might say that x equals 2i. Now, if I just said x equals 2i, that would be an answer choice, but it'd be wrong. What would you need to have if you have an x equals 2i? A positive and a minus. Now, to finish this problem, it says, can you give me 2 different examples of factors? So what would that look like as a factor? As a factor, that means in parentheses. It would be what in parentheses? I'll go in order. If this first one was x equals positive 2i, you would rewrite it as x minus 2i, and then the x equals negative 2i would become plus x plus 2i. Do you remember what happens if you multiply those out? I know it doesn't ask us to do that here, but you have to do it. So I'm going to go ahead and do one here. I'm going to do a box method real quick. Do you remember what will happen to the i's every time if you do this correctly? They'll cancel out. So I'll go ahead and I'll write the first factor on the top, x minus 2i, and on the side, x plus 2i. It doesn't really matter the order you go, but I'll do that. What is x times x? X squared. What is x times negative 2i? Negative 2ix. What about positive 2i times x? Positive 2ix. And then positive 2i times negative 2i. Minus 4i squared. If you do your math correctly, your I should always cancel out. I see these 2 obviously cancel out, but here we need to remember something. If I was originally the square root of a negative number, negative 1, that meant I squared was equal to negative 1. So what is negative 4 times negative 1? Positive 4. This is equal to positive 4. You could cancel that out and say that's equal to positive 4. So rewriting this would be equal to x squared plus 4. These are zeros. I'm just going to put y equals on the front here and y equals in the front there. So you can see that would be the graph that would produce those zeros of 2i and negative 2i. It's a parabola that's been shifted up 2 units. Okay, now it's not just imaginary zeros that have conjugate pairs. What also have imaginary pairs? You remember it started with an I as well. Irrational. And there were irrational numbers we gave you last time we talked about in that lesson. We said pi is 1, but what do most of them come from? Square roots. So if you saw you had an answer, the square root of 5, what else? What would you also have? A positive and a negative version of the square root of 5. And so as factors, what would that look like? x minus square root of 5 times x plus square root of 5. We could do box method. But since they're difference of squares, I'm going to just go ahead and tell you that these two would cancel out just the same. When you multiply this x times the positive square root of 5 and then the negative square root of 5 times this x, those two would cancel out. So what you would be left with is the x times x, which is x squared, and then negative square root 25 times positive square root 25. What is negative times a positive? Negative square root of 25, and you could simplify that one more time. What is the square root of 25? 5. This would be x squared minus 5. That would be that equation. You could do a box method. I just skipped it. But that's what that would be right there. That's where that would come from. So this one would have two real zeros. They are real. It would hit the x-axis, but they would hit at these irrational values of positive and negative square root 5. So that's what has conjugate pairs. All right, our last question. Last question here on this review. It says the function y equals f of x is shown. Question, on what intervals is f of x? Someone read this symbol. What is that in English? Greater than or equal to 0. What would you be looking for in the graph if you're looking for greater than or equal to 0? Where is it positive? Where is it above the x-axis? So it looks like to me that we have how many zeros? 3. To be positive means you're above the zeros. To be greater than or equal to 0 means you would include them. What x value is that? Goodness gracious, I didn't give a good number, did I? What was I doing? I don't know what I was thinking here. Why did I put that as an equation? Well, let's just say that value is at, what do y'all want to guess that is? Y'all want to call it just -1 or you want to call it -1.2? Y'all just want to call it -1? All right, we'll just say it's at -1. Let's just say that's at -1, this is at 1, and this is at 3. Y'all want to do that? So what intervals is f of x greater than 0? How do you write intervals again? X values. What x value do we start at? -1. Since I can be equal to it, I'll do a bracket. From -1 until when? 1. That area, you are greater than or equal to 0, and you do a union from 3 until where? Infinity. Infinity always gets a parenthesis, never a bracket, because you cannot be equal to infinity. So this is the part of the graph where it is above the x-axis. So this is where it's positive because it's above the x-axis. Just to make sure you're aware of that, that's where that answer would be. It's because that's where it's above the x-axis. Okay? And now moving on, the next one. What intervals is the graph concave down? So show me concave down with your hands. How many spots will your hand be able to put on that graph like that? 1. From where to where? Ooh, not -1. Don't stop there. This is all still concave down. So from negative infinity until? Good. Negative infinity until 1. So negative infinity is in parentheses. With concavity, you can always use parentheses if you want. Just go like that. From negative infinity until 1, we are concave down. So this part in here is concave down. What intervals is f of x increasing? What's it doing at the start? Increasing until here. Let's just call that a half. Y'all want to call that or negative half? Let's call it negative 0.5. From negative, I didn't put the y value. What's that y value? Do you want to call it 4, like 4.5 or 4.2, or what do you want to call that? 4. Okay, let's call it 4. On what intervals is it increasing? What does intervals mean again? X value. You only list x values. From where to where? Negative infinity to negative 0.5. Does it increase anywhere else? All right, from this point on, let's call this one 2.5. And I'll call it -4. From 2.5 on, it increases. So we'll say union from 2.5 until infinity. Finally, if g of x equals this, okay, what is it saying? If g of x is equal to the a rock, what is the parent function of g of x? So look at this function. What type of function is this? It is odd. What's the simplest odd that has 3 zeros? I should have put that. If all the zeros are shown, this would be cubic. If f of x is cubic, what and g of x is its a rock, what does that mean g of x is? Quadratic. And therefore, the parent function would be y equals x squared. That's the most basic. Parent function means the most basic. It would be x squared. So I'm missing some words in there. It should say, if all the zeros of f are shown, if all the zeros are shown, what, and g of x equals this, what is the parent function? And that would be it. Okay, that's a wrap. You have delta math you can work on. That is everything on the packet, correct? Okay, go to your delta math. You have some time left over to work on that.